Intermediate System to Intermediate System, ISIS, serves as a Link State Interior Gateway Protocol, IGP, facilitating the exchange of routing information among routers within a network. The primary function of ISIS lies in the sharing of network topology data to enable the determination of optimal data paths. Typically implemented within a single autonomous system, ISIS finds prevalent usage in extensive enterprise and service provider networks. As a standardized protocol outlined in ISO IEC 100589-2002, ISIS operates as an international standard within the framework of the Open Systems Interconnection (OSI) reference model. Within the realm of interior gateway protocols, ISIS is tailored for deployment within an administrative domain or network environment, distinct from exterior gateway protocols like the Border Gateway Protocol, BGP, which route between autonomous systems. Functioning as a link state routing protocol, ISIS propagates link state information extensively among a network of routers. Each ISIS router constructs its individual link state database, LSDB, by amassing the distributed link state details from fellow routers. Similar to the operational premise of the OSPF protocol, ISIS leverages Dijkstra's algorithm to compute the most efficient path across the network. Subsequently, packets are forwarded based on the calculated optimal path to reach their intended destinations. Historically, the inception of the ISIS protocol traces back to its development by a collective effort at Digital Equipment Corporation within the framework of DECnet Phase 5. The Internet Engineering Task Force, IETF, brought ISIS to light in 1990. However, the RFC publication encountered retraction, marking it as historic due to inadvertently republishing a draft version of the International Organization for Standardization, ISO, standard rather than the final iteration, leading to confusion. ISO proceeded to standardize the protocol in 1992 as ISO 10589, envisaging communication among network devices termed intermediate systems within the OSI structure. At its core, ISIS aimed to enable datagram routing using the ISO's Connectionless Mode Network Service (CLNS) protocol stack. Concurrently with the development of OSPF by the Internet Engineering Task Force, IETF, ISIS underwent extensions to support datagram routing over the Internet Protocol, IP, evolving into integrated ISIS. By 2005, ISIS had firmly established itself as the industry standard for large-scale service provider network backbones. The ISIS protocol introduces its unique terminology encompassing network elements, deviating or offering less conventional terms compared to prevailing industry standards. Essential ISIS components like intermediate systems, designated intermediate systems, and end systems occupy pivotal roles within the network fabric. The concept of circuit delineates Layer 2 broadcast domains encompassing diverse configurations ranging from point-to-point connections to local area networks, ADLANs. Adjacent routers, referred to as adjacencies, engage in the exchange of routing intelligence. ISIS's packet types encompass Hello Protocol Data Units, PDUs, Link State PDUs, LSPs, Complete Sequence Number PDUs, CSNPs, and Partial Sequence Number PDUs, PSNPs, structured to support efficient information dissemination and network operation. In ISIS addressing, a departure from traditional IP routing protocols is evident, with ISIS operating directly over Layer 2 without relying on Layer 3 transport and refraining from using IP addresses to identify individual intermediate system interfaces. Instead, ISIS adopts the ISO network address paradigm, assigning distinct ISO network addresses like Network Service Access Points, NSAPs, to each connection point within the autonomous system. Individual intermediate systems receive network entity titles, NETs, comparable to NSAPs, albeit with variations, to facilitate differentiation and network orchestration. Encouragingly, the alignment of the system ID field with a unique IPv4 address assigned to a router's loopback interface signifies best practice within the ISIS protocol landscape. The consideration for streamlined hostname resolution strategies underscores the practicalities of managing expansive networks effectively. While conventional routing protocols rely on IP addresses for router identification, ISIS integrates hostname resolution intricacies within its standard framework. Incorporating link state PDUs with type length value, 137 TLV 137 fields, capable of housing host names associated with nets, ISIS pioneers hostname resolution within its operational scope. Areas and levels in ISIS, mirroring the architecture of OSPF, serve to partition networks judiciously, enhancing router efficiency by minimizing the burden of maintaining complete link state information across all nodes. The classification of routers into Level 1, Level 2, or Level 1/Level 2 entities underscores their respective roles in intra-area routing, inter-area connectivity, and boundary routing operations within the ISIS network fabric. Adherence to specified attribute bits within ISIS, link state PDUs denoting functionalities like partition repair, attach status, overload indication, and IS type classifications contributes to optimizing network performance and operational resilience within the ISIS ecosystem. When ISIS was first introduced, there were limitations on interface and path metrics to accommodate the network dynamics of that time. However, as networks expanded and technology improved, these constraints became insufficient due to increased speeds and hop counts. To address this issue, 2 new TLVs were added to the protocol: TLV 22 for extended IS reachability and TLV 135 for extended IP reachability. These additions allowed for larger metrics, with link metrics now reaching up to 16.7 million and total accumulated path metrics up to 4 billion. Metrics without TLV 22 and 135 are considered narrow, while those with them are dubbed wide. These metrics can be set on a per-level basis. In terms of adjacency formation, ISIS has simpler rules compared to OSPF, largely dependent on the router level. For instance, an L1 router cannot establish adjacency with an L2 router. However, an L1 router can form an L1 adjacency with another L1 router in the same area, and with an L1 or L2 router in the same area as well. On the other hand, an L2 router can establish a L2 adjacency with other L2 routers, regardless of their areas. Furthermore, a designated intermediate system, DIS, is elected in broadcast segments to facilitate efficient communication among routers. The DS acts as a hub with other routers forming adjacencies solely with the DS, reducing the number of adjacencies that need to be maintained. Authentication in ISIS supports both simple password and MD5 authentication types, allowing for per-level or per-interface authentication. Additionally, to prevent replay attacks, ISIS employs an increasing sequence number in the IIH. Unlike OSPF, which operates at Layer 3, ISIS encapsulates its PDUs into Layer 2 frames independent of Layer 3 protocols. To support IPv6 routing information, TLVs for IPv6 interface address and reachability were introduced. ISIS path selection utilizes Dijkstra's algorithm to generate routing tables, prioritizing paths based on a specific order in various scenarios. BFD support enhances fault detection by operating independently of the routing protocol and enabling sub-second detection with minimal CPU impact. ISIS's role extends to being the foundation for shortest path bridging, SPB, facilitating equal-cost multipath routing among Ethernet switches in a mesh topology. This extension of ISIS incorporates new TLVs to support SPB functionalities.